For page 6, remember the word net means gain. So if you have like a net, or loss, so it's change. So net's change, not total. So is there any gain or loss momentum? The answer is no. We never have gain or loss momentum. It's always going to be conserved. So whatever we gain from one body is lost from the other body. So for example, like when there's a net profit, right? That's that means you made money, or you could have lost money too if you spent more than you collected. So in this case, Suki is right. Yes, because momentum is conserved. This means there's no gain or loss of momentum. The momentum transfer to the system is zero. If the net momentum, is zero. What does that imply about the total system momentum before and after? They'll be equal, as we see over here from the two-cart system bar graphs. They will be equal. And then what does that imply about the momentum transfer to cart 1 compared to cart 2? Well, we see that they're going opposite directions. So they'll have the same magnitude, but they'll be opposite in sign. So that's what we expect there. So whatever you lose from one, you gain from the other. So overall, it's for the system, the net momentum is zero. So that's what they're trying to get across with page 6. Now for page 7 here, you did have to fill out the bars. I forgot to mention that before we left the breakout rooms, but I did tell each group in the breakout rooms that you have to do. So you see that if you count this, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 boxes to the right for cart 2. Those 9 boxes to the left for cart 1. Then for the final momentum, you basically take the difference between the before and transfer. So 8 minus 9 is -1. So momentum is -1 for the first cart, the final momentum of the first cart. The final momentum of the second cart is going to be 9 because initially it had nothing and it gained 9. That's why it's 9 for the final momentum of cart 2. But the overall momentum is going to be 8 because it was 8 before. So if you look at P1 initial plus P2 initial, 8 plus 0 is 8. But here you're doing 9 plus -1 is also 8. So you expect that to be conserved. Because the mass, because the initial velocity was 2 meters per second for cart 1, its mass is 4 kilograms. Cart 2 had triple mass, it's 12 kilograms. So if you kind of consider that carefully, because your momentum was -1 here, right? -1 is going to equal your mass, which is 4, times your velocity. So your velocity is -1/4 for cart 1. So it's actually going to the left, as we see right there. For here, because our final momentum was 9, great, that on me again, is 9, and the mass is 12. When you solve for that velocity, you're going to get 3/4 or 0.75. So they move quite slowly. And actually, let's prove it through the simulation. Let's actually get this going here. So if our elasticity is 1, initial is 2, and here it's 0. And let me triple mass of that one, play it. Actually, oops, the elasticity was 0.5, my bad. Let's try again. There we go. So that's what we notice what happens. Then going back to, yes, over here. So that's what we have there. And then going back to my images. For case 3, again, doing the same masses, the same speed for cart 1 going to the right. So now the net loss was 6 for cart 1, but net gain is 6 for cart 2. 8 minus 6 is 2, so you have 2 here, but here 6, 0 plus 6, so you get 6. But overall, the total momentum before and after is going to be 8 and 8. It is conserved. And again, if you do here, 2 equals your mass times your velocity. Here, your momentum is 6, your mass is 12 times velocity. And they're going to stick together because it is completely inelastic. They're going to go at the same velocity and sticking together. And the thing is, the momentum transfer change is the same for all 3 cases. So whatever you gain from one, you lose from the other in the opposite direction. That's always going to be true for any type of elasticity you're dealing with, or inelasticity. We'll just run through that simulation really, really quickly. So let me clear my screen. So if I do this again, but now I go to 0 and play it. Let's stick together as 0.5. So hopefully that makes sense for that one. Okay. So once you guys get your notes out again, we're going to talk about 7.3. We've got about 30 minutes left. Problem sets 7.3. Give me 1 sec. Just got to grab from the printer. Okay. Let's talk about 7.3, about sound. So I'll probably give you a video a little bit on this, and then also some stuff on circuits tonight, and then we'll kind of move on to something else tomorrow. So how is sound made? So some vibrating object, actually, hold on. Let me record this. We're still recording? We're still recording, great. Some vibrating object, like a speaker, moves and vibrates the air. If you wanted to test this out, you could go outside and blast a stereo in your car. Your parents probably not be too happy about that. If you made it while your neighbors would be pretty upset. But you would feel rattling, right? We kind of would expect that. So air pressure rises. That's called condensation. That's not working. And you can see from the diagram again, we have like the spring, like a slinky, I guess. Think of sound doing the same thing. Where it seems to be dense is kind of like what we're hearing with a vibration. But anyway, when air pressure rises, we call that condensation. So hard to write with your mouse. Condensation moves away at the speed of sound, so follows the speed of sound. Objects moving back, creating less air pressure. That's called rarefication. So these are some more facts. Not again, we're not doing a test this week, so I'm going to combine the stuff with next week. But I'm not going to really ask these kind of items here. I'm really more curious about the quantitative stuff. But rarefication moves away, also the speed of sound. Particles, move back and forth. And this between consecutive constant rarefications, we call that the wavelength. So that's what's happening over here. So we call it the wavelength. String or speaker makes air molecules vibrate. So a string or a speaker. That molecule pushes the next one to vibrate and so on. So kind of that's what you're seeing over here. So one molecule pushes another molecule and they vibrate. And when it hits the ear, when you finally hear the sound, the vibrations are interpreted as sound. So that's how sound is produced. So again, we think of sound as like air vibrating. Now let's talk about some other things here. Let's talk about pitch. One cycle. So you see here, this counts as one cycle. Basically, it has condensation, which is when the air pressure is rising, and rarefication, when an object moves back, creating less air pressure. So when it's rising, it's condensation. When it's going down, it's rarefication. So one cycle basically is one region of condensation, or basically you're getting like, the very condensed amount of particles, which I guess you could think of as that right there. And rarefaction where you're getting a little bit less air pressure, which is kind of like that. And the combination of that's one cycle. Remember, frequency, number of cycles per second. Each frequency does have its own tone. So that's when if you play music, or you're on a piano, that's another good example, is that they all kind of sound differently because of their frequencies, right? So different frequencies can create different sounds. So sounds with one frequency are called a pure tone. Healthy young people, so if you haven't damaged your eardrums. Pure frequency of 20 to about 20,000 hertz. Brain can interpret frequency as pitch. Any questions so far? So I'll have to move the screen. Another thing to keep in mind is that in Campbell, our new building, which we haven't really been able to enjoy lately. If you ever go to the music room, they got pretty good soundproofing in there. And mainly because, they don't want to disturb other people, but also to protect the ears of the people who are in there, especially the band teacher who's there for like a certain period of time. Not sure if you guys remember, but when we were in the portables, the band liked to keep doors open, and we math teachers didn't like it because it was very disturbing for us. But we understood why they had to do it, because they didn't soundproof the portables. Obviously, it's cheap portables, right? I think they put up curtains. I think that helps some with absorbing sound, but you get, the sound waves hit the wall and then come back at you, and so you have that, they call it reverberation, and that can be very damaging to your ears when you hear that for a prolonged period of time. That sometimes your ears start ringing. That's not a good thing. You don't want that to happen. So like going to concerts, they're fun, but sometimes you kind of want to not be too close to those big speakers, or at least have earplugs. If you go to or the Spirit Week, when there's a lot of cheering and loud noises. So you're realizing these are vibrations are happening, and you guys are very, very familiar with this stuff. So again, brain can interpret frequency as pitch. So you can have high pitch, which can be very hard in the ears. So high frequency equals high pitch. Usually my little children, they tend to have high pitch when they're crying. So, and subjective, it's subjective. Because most people don't have a perfect pitch. Like we don't know what is considered like the perfect frequency to listen to. Loudness. Condensations have more pressure than rarefication. So the air, when sound's traveling, the air can be very condensed and also rarefied. Amplitude equals the highest pressure. So when sound is traveling, it's going to be kind of like that. Typical conversation, usually about 0.08, sorry, 0.03. And by the way, we haven't talked about this. This is a unit for pressure. It's called Pascal. Pressure, just is force divided by area. You tend to learn more about this when you start doing like fluids and gases, but we're not going to do that in this class. Atmospheric air pressure has a lot of pressure, about 101,000 pascals. So, and loudness, so the pressure of air is much, much greater than our typical conversation. Loudness is the ear's interpretation of pressure amplitude. Speed of sound we talked about was about 343, 344 roughly. So for all waves, the formula is this. We know this, right? Velocity equals frequency times wavelength. Sound travels slowest in gases. Faster in liquids. And fastest in solids. So you expect speed of sound to travel faster with those mediums as you go from gas to liquids to solids. Around 20 degrees, that's the speed of sound. So when you hear about like airplanes breaking the sound barrier, that's what we're talking about, going at that speed. I believe like Mach 1 is going at that speed, and the Mach 2 would be double, if I'm not mistaken. Speed of sound does depend on the medium, what you're traveling through. In gases, air is a gas. Sound streams are the only ones the molecules collide. So we derive the formula for speed from the speed of molecules. And speed changes with temperature. And there's a formula here. If you had chemistry, 273 Kelvin, hopefully you know 0 degrees Celsius. So if you're in 20 degrees Celsius, then you put in 293 for Kelvin, or for capital T. Any questions so far? And this speed of sound through a lot of different things. So it's just kind of a little table there. And T is in kelvins. So let's do a couple examples and we'll wrap it up for today. And we'll do actually these problems in class tomorrow. All this stuff here. And then we'll also talk about circuit. And we're not going to do any more lab stuff. We'll get heavy with circuits. And we'll do more circuits on Thursday. And then we're not going to do a test on Thursday. Okay. Let's look at this one here. What wavelength corresponds to frequency of a concert, which is 440 hertz if the air is 25 degrees Celsius. So let's figure out our velocity. And remember, velocity 331 times square root. Now our temperature is 25. So I'll have some people help me out here. So let's go with Elizabeth, I'm calling you. If we have 25 degrees Celsius, do you know what that will be in Kelvin? No, remember 0 degrees is 273 Kelvin. So what do you think 25 would be in Kelvin?
I'm not sure.
Well, do you know the relation between the two?
Oh, yeah. Don't you like add 273.15?
You know, I knew you knew it. I just wanted you to tell me. Good. So 298. Good.
15.
Yeah, it's not a proportion. Just you just add on.
That's right. Yeah.
Celsius and Fahrenheit they're not really proportionally, but they have another kind of formula. So good. So we'll calculate this first. And remember, velocity equals your frequency times your wavelength. So if I work that out, root 298 divided by 273, you get 1.045 times 331. So about 345.82. So now if your velocity is 345.82, geez, 345. And your frequency is 440 hertz, we can now solve for lambda. And the wavelength, if you do it correctly, should be 0.786 meters, mind you. Meters. How far is a ship if it takes 3.4 seconds to receive a return signal in sea water? Okay, well, we have a table here. What's the speed of sound in sea water? looks like it's 1540. So you want to use a table for that. You could use that, but because it's dealing with velocity, we're going to just do this. Your displacement, your position is velocity times time. So your velocity is going to be 1540. That's meters per second, mind you. Times 3.4 seconds. And it should be about 5,236 meters. However, to receive a return signal, right? So you get the signal, you return it back. So you actually have to divide that by 2. It's going to be 2618. So that's that one there. So again, these calculations are pretty straightforward and not really too bad. You guys could probably knock out 5, 6, 7, or 4 through 8. This is 6:30, 7:1. Okay. So we'll just do like a 5-minute breakout room.